Hello everyone, today let's take a look at QP10, another simplification slash recursion type of brain teaser, kind of a follow-up to QP16, the same kind of idea. So essentially we have 5 pirates who loot this chest full of 100 gold coins. They agree on the following method to divide the loot. The oldest pirate proposes a distribution, and then all of the other pirates will basically vote on whether or not to accept his proposal. And the oldest pirate, the one who proposed the distribution, is allowed to vote as well. So if at least 50% of the pirates vote in favor, the proposal will pass, and if not, the oldest pirate is killed and the process starts over with the next oldest pirate. And again, all these pirates are rational, so they have the following priorities, right? First of all, they want to stay alive with highest priority. They want to get as much gold as possible with second highest priority, and they want to have as few pirates on the boat as possible with third highest priority. So how will the coins be divided in the end? So again, you can see how this is a pretty similar setup to what's going on in QP16. In this case, we have 5 pirates. Again, for every single problem, we're just going to want to start from a simpler case. So let's start from the situation where we have 1 pirate and he finds 100 gold coins. So now he's obviously going to be the oldest because he's the only pirate. So he proposes the distribution. So now he needs at least 50% of the pirates to vote in his favor. In this case, there's only 1 pirate, and he's obviously just going to vote for whatever he proposes. So he can just give himself all 100 coins. He's just going to say, I take all 100 coins. I mean, that's the only thing that could happen anyways, right? So in the case when there's 1 pirate, he finds 100 coins. He's just going to take all 100 coins from himself, and there's no one around to stop him. So now if we have 2 pirates, let's look at that case now. Now, if I have 2 pirates and they both find 100 coins, okay, let's say this guy right here is the oldest, and this one is the younger one. Now, he's going to propose the distribution of coins. So they find 100 coins, and now notice that he can just still give himself all 100 coins, right? This guy is not going to like it. He's not going to vote for it, but the pirate only needs 50% of the available vote, and the oldest pirate gets to vote himself, right? This pirate right here is going to propose all 100 coins be sent over to him, and then this guy will get 0. That's going to be his proposal, and this guy's not going to like it. He's going to vote against it, right? But it doesn't matter because this guy will vote for it, and he has 50% of the available vote, so it's going to pass. So in this situation, when we have 2 pirates, the oldest is going to be able to get 100 coins, and the other person is just going to get 0 coins, right? That's going to be our distribution. Okay, now let's look at the situation when we have 3 pirates. We're slowly working our way up to when we have 5 pirates, right? Now, this is our oldest pirate right here. This will be our second oldest, and then this will be our youngest pirate. Now, notice if the oldest pirate proposes that he gets all 100 coins and the other 2 get 0, well, they are both not going to like that, right? So they're both going to vote against that proposal, and then in this case, they're going to have the majority, right? They're going to have 2/3 of the vote. And the oldest pirate is rational, so he does not want to die, right? If he proposes a distribution such that the other 2 vote against it, well, then he's going to die. So his highest priority is to stay alive, so he does not want to do that. So this pirate right here, he's going to have to basically come up with a distribution such that one of these pirates will end up voting for him, right? Because he just needs 1 other pirate to vote for him in order for his proposal to pass. So who can he be able to convince in this situation, right? Well, this guy right here, the middle oldest guy, he knows that if this pirate dies, the oldest one, well, then he's going to wind up as this pirate in the situation when there's 2 pirates left, right? So he knows that he's about to wind up in this situation if the oldest guy dies, and in this situation, he knows that he got 100 coins all to himself. So this guy's really incentivized to kill the pirate so he can get all 100 of these coins for himself, right? So this guy is essentially impossible to convince to vote for your proposal, right? But what about this guy, the youngest guy? Well, the youngest guy knows that if the oldest pirate is killed, well, then he's going to wind up as the younger guy in this situation when we had 2 pirates, and in that situation, he got 0 coins. So all the oldest pirate has to do is basically he can give himself 99 of the coins, right? And then he's just going to give 1 coin to the youngest pirate, right? Because the youngest pirate will now vote for him if he gets 1 coin, because in his eyes, 1 coin is going to be better than the 0 coins he's going to get if the oldest pirate dies. You notice that it didn't work when he gave himself all 100 coins, because in that situation, this guy would be getting 0 coins, but with third highest priority, right, they want to have as few pirates on the boat as possible. So this guy's still going to prefer getting 0 coins in the situation when there's 2 pirates over getting 0 coins in the situation when there's 3 pirates left, right? But since each of these pirates' second highest priority is getting as many coins as possible, right, well, this guy right here knows that 1 coin will be better than 0 coins, so he's going to be incentivized to vote for this pirate's proposal when he does 99 and 1. So that's what the pirate will propose, and that will get through, and he will get 99 coins. So that's a solution when there's 3 pirates. The oldest just needs to propose this distribution right here, where he gets 99 coins and the other person gets 1. So now let's look at the 4 pirates case. We're slowly building our way up here. Now if I have 4 pirates, let's say this one's the oldest, this is the second oldest, this is the third oldest, and then this is the youngest right here. Let's see what will happen in this situation. Obviously, just like the last situation, this oldest pirate here will not be able to give himself all 100 coins because everyone else is going to vote against it, and then he will die. So he's not going to want to do that. But since the oldest pirate only needs 50% of the vote in order for his proposal to pass, right, he only needs to convince 1 of these other 3 people to vote for him because his vote counts as well. So he's going to ask himself, which out of these remaining 3 pirates do I have to give the least amount of coins to in order for them to vote for me, right? So let's look at this guy right here. Is he incentivized to vote for this top pirate? Well, again, all these pirates are rational, rational. So this guy right here, he knows that if he kills off the oldest pirate, well then he will now become the oldest pirate in the next situation, right? And in that situation, he got 99 coins, right? So he's going to need more than 99 coins in order to convince him to vote for that pirate. So that's not very good. Now for this guy, the third oldest pirate, he knows that if he votes against the pirate and the oldest pirate ends up getting killed, well then he's going to wind up as the middle pirate in the situation when there's 3 pirates, right? Now the middle pirate in this situation got 0 coins, so he's pretty easy to convince because he knows that he's going to get 0 coins in this next situation, right? This shouldn't say other here, this should say the youngest gets 1 coin and then the middle will get 0 coins. That was the previous proposal. So this guy is going to wind up with 0 coins if he kills the top pirate. So basically all the oldest pirate needs to do is just propose a distribution where now he gets 99 coins and then he gives 1 coin to this guy, right? And now this guy will vote for him because he's going to be getting 1 coin as opposed to 0. Now when the oldest pirate proposes his distribution, he's going to vote for it himself and this guy will vote for it too, so he's going to have 50% of the vote. So this is what's going to happen. The oldest will get 99 again, and then basically this guy, the third oldest, will get 1. Okay, so we figured out the distribution for 4 pirates, so now all we have to do is figure out the distribution for 5 pirates, which is what the question was actually asking us originally, right? And then that will basically end our search for the distribution. So these are our 5 pirates here. This is the oldest, second oldest, third oldest, fourth oldest, and the youngest here. What's going to happen? Well, now that we have 5 pirates, the oldest knows that he needs 2 of the remaining 4 pirates in order to vote for him in order to cross the 50% threshold. So now he needs 2 remaining votes, so he asks himself, who are the easiest to convince? So let's look at this guy first. Is he easy to convince? Well, not really, because this guy knows that he's going to wind up, if he kills the oldest pirate, as the oldest pirate in the situation when there's 4 pirates, and in that situation he got 99 coins, so he's not easy to convince. Now let's look at this guy. Well, this guy knows that if the oldest pirate dies, well then he's going to wind up as this guy in the situation when there's 4 pirates, and in that situation he got 0 coins, so he's relatively easy to convince. So this should be one of the pirates that we give 1 of our coins to, right? Now let's look at this guy. We still need 1 other pirate. Now this guy right here, he knows that he will wind up, if he kills the oldest pirate, as this pirate in the 4 pirate situation, and in that situation he got 1 coin, so he's going to need at least 2 coins in order to convince him to vote for this oldest pirate's distribution here. So this pirate could convince this guy to vote for him by giving him 2 coins, but that's not going to be the best that this pirate can do, because we can still convince this pirate instead, right? And then this guy will end up getting more coins. Why? Because this pirate here knows that he will wind up, if the oldest pirate dies, as the pirate right here in this situation, right? He's going to wind up as the youngest pirate, and the youngest pirate got 0 coins in the 4 pirate case. So this guy right here knows he's getting 0 coins if the oldest dies, so he only has to give that pirate 1 coin. So he's going to give 1 coin to that pirate, 1 coin to this pirate, and then they're both going to want to vote for him, and then he will get the remaining 98 coins. So that's the final answer to this question. That right there is the distribution where this pirate stays alive and he winds up with the most amount of coins as possible. So what is it? The oldest basically got 98 coins. The third oldest, right? The third oldest got 1 coin, and then basically the youngest got 1 coin as well. So that is the final answer to this question, the best possible distribution for the oldest pirate in the 5 pirate case. You can see when you start simple and you just work through all the cases, these problems really are not that hard. So we're just using simplification here and basic properties of recursion, right? When they're all rational, they all understand the situations before them. So if you ever see rational, that's basically what that means.